Hello, my name is Pablo Halpern. I am a parallel architect at Intel, which means I kind of coordinate the development of parallel languages among many groups at Intel. We're going to be talking today about decomposing a problem for parallel execution. So how do you break things down so you can run multiple parts in parallel? I have to remember that this thing doesn't click. Our goal is to sort of learn how to break down a problem so that you can run the different parts in parallel. I'm going to be moving pretty quickly, so if you have a question, ideally get to the mic, but at least make some signal that I need to pause. Okay, but ask the questions as we go along, it's fine. Okay, so we're going to be looking at two problems and kind of diving into the actual code of how you parallelize these problems. The first one is a pretty simple one. That's counting the number of stars in an image. It's pretty easy, but it does expose certain issues. They're best described in an easy situation. And then we go into a little bit more involved problem, the nbodies problem, and show that you can get only so far with certain techniques, and then you have to like rethink some things and maybe restructure certain parts of your code. So the last bit is very cool, the restructured stuff, so make sure you stay to the end. All right, some principles. When we're parallelizing code, the main challenge is to find the tasks that can execute without dependencies on each other, or with minimal interaction with each other. The process should be fun. It's kind of this new dimension on programming where you get to apply your creativity to, get the problem solved. There's a lot of measuring, there's a lot of testing, iterating over the process. Let me talk a little bit about what parallelism is, how it's expressed mathematically. This is a graph of the dependencies, or the flow, really, among different tasks in a program. What each of these bubbles represents is a task. And if two bubbles are connected by an arrow, it means the first one must precede the second one. So A precedes B, and mathematically we write it this way. This is not a less than symbol. This is a special symbol that means precedes. And if those of you, how many people worked my earlier talk yesterday? Oh, a lot of you. So this wouldn't be new to you, but I'll just very quickly go through it for everybody else. This graph also tells us that F and B are in parallel with each other. That's what this symbol means. And that K is in parallel with H, and K is also in parallel with B and C, and so on. You can see that from the graph, that there's no forward arrows connecting connecting B to K, and therefore they're in parallel. I'm going to be using Silk Plus as the language for teaching this. Silk Plus is a particularly easy notation to learn, and it's available in the GCC compiler in a branch of Clang. It's available in the Intel compiler. It's not the only language, but it's the one I'm using for teaching here. Just to understand what's going on here, what we have here is a recursive Fibonacci calculation, the worst way possible to compute Fibonacci. And the spawn says you can continue to execute the thing that follows the spawn without waiting for the spawn function to complete. All right? So this creates a task, and it says these two tasks can execute in parallel. The sync says we're done with parallelism, that anything spawned within the same function must be done before we continue here. Simple fork join. There's an implicit sync at the end of the function for what it's worth. The Silk for is another fork join construct. It says everything inside the for is done in parallel. In fact, never make that mistake. In parallel does not mean simultaneous necessarily. So the iterations of the for are all in parallel with each other, which means they are, at least the programmer is asserting that they are independent of each other and can be executed in any order and simultaneously if there's resources to do it simultaneously. Notice I highlighted aloud. And when you're writing parallel programs, what you're trying to do is annotate where are things logically parallel. It is then up to the runtime environment to figure out what can actually happen simultaneously. If you've got 1,000 CPUs, a lot more will happen simultaneously than if you've got 2. The idea is you do not create 1,000 threads on a 2 CPU system. You don't create any threads. You let the runtime system create as many threads as makes sense, which on a 2 CPU system might be 2, might be more than 2, might be 2, might be 1, and execute things as resources allow. So just because things are notated as being in parallel does not mean they're going to run simultaneously. It's a load balancing thing and the runtime knows best. Okay, so let's get to our first example. We've gotten through the preliminaries. The star counting problem. We're going to talk about what the problem is. We're going to look at how you would implement it serially. And then we're going to implement it in parallel, fix a race condition that we've introduced, and then we're going to find a better way to express the loop. This is the problem. Count the number of stars in this image. This is a real Hubble telescope image of stars. How would you go about this? Well, the most straightforward way is to write a loop that says, let's go over every pixel, and if that pixel represents the middle of a star, I'm hitting the wrong button, then if it's center of star, then we increment the count. Now this is how I conveniently left out the details of how we figure out if it's in the middle of a star. That's not my problem, okay? Not my area of expertise. Suffice to say that it would require seeing not only the pixel in question, x and y, but probably all the pixels around it. At least 9 pixels and probably more. Every time we find one pixel that is the center of a star, we say, all right, we'll increase our count, and at the end we return the total count. All right, so just note the disclaimer here, I haven't actually written this code. All right. I would have if I had more time. But if I had more time, I probably would have written a bigger talk. So, okay. So now let's take a look at this algorithm and see where is the parallelism. Well, what you want to find is what can happen independently. And when you see a loop, you immediately think, can the iterations be executed in parallel? Well, finding the center of the star is almost certainly a completely independent operation because you're reading the pixels. You're not even modifying them. So you should be able to check all the pixels at the same time if you have enough compute resources, right? Increasing the count, well, counting is independent. You can count on multiple CPUs at once. But the problem is updating the single variable. So when we try and parallelize this in the most obvious way, which is to use these silk for loops to make these loops parallel, it almost works, but we end up with the problem of parallel updates to a single value, okay? And that's a race condition. So a race condition is defined as multiple parallel or concurrent strands accessing the same memory location where at least one of them is a write. And in this case, they're all writes. In fact, they're all read, modify, writes. That's what an increment is. All right, so we have a correctness problem. Okay, data races and indeterminacy races in general, which is a generalization of the idea of a data race, is one of those real correctness bugs, one of the few real correctness bugs in parallel programs. There's a lot of things that will interfere with getting good performance. Data races interfere with getting the right answer. So you want to fix those pronto. So our first solution, which some of you may have already thought of, is how about we use atomic variables? Atomic variables can be incremented in more than one thread at the same time. So having them executed in parallel would seem to work. And it does. This will actually do the job. The problem with these variables is that you have a contention problem on the shared variable. The contention problem is not, if you have a big black area with a few dozen stars, you won't notice the contention. If you have the picture that we just showed, you'll probably notice the contention. And the more CPUs you have, the more contention you'll notice. Why? What's going on? Keep clicking this thinking it's going to advance. This is what's happening when you access an atomic variable from more than one thread. and especially if it's happening frequently. Okay? What we're doing here is each thread is on separate pixels, computing is it the center of the star. If it is the center, it increments the count. Then it goes back and says, is it the center of the star? And if it is, it increments the count. Okay, it's doing this over and over again. Another CPU is doing the same set of operations, okay, on different pixels. The problem is that when this guy wants to increment the count, he has to say, wait, this is mine. There is an invariant that says a location can be in one L1 cache in modifiable state at a time. So you've got two CPUs here. It cannot be modifiable. Count cannot be modifiable in both CPUs at the same time. So what happens is every time one of them modifies it, it has to send a message via a couple of wires on the integrated circuit if you're lucky, or it goes to the actual circuit board if you're on separate sockets to communicate, hey, if you have this in your cache, you have to invalidate it. So every time one of these guys increments count, it invalidates a cache line in the other guy. And every time he wants to get it again, he's got to read it back from main memory or from whatever the most common shared cache is, and wait until it's there. Okay, there's a latency involved reading it again from memory. So you've got two forms of slowdown here. One is the actual inter-CPU communication, and then the other is the latency on the rereads. Okay, so the question is, and in the future, people, please queue up on the microphones if you want to. The question is, what happens in hardware if they both want to do it at exactly the same time? Well, that's a hardware problem. We're in software group right here, but so I know that's a glib answer. So I don't know at a very, very detailed level. I can say that nothing ever exactly happens at the same time in the hardware. The hardware really has these, it has specific circuitry to randomly pick a winner when there's an actual two signals arrive effectively simultaneously. It's not complicated circuitry, I don't think, but it's there. Something's going on there. One of them will. Okay. Yeah, right. Right. That's yeah. Well, I like the answer of don't worry about it. Okay, so that's, yeah. Okay, so this is why atomics are not a panacea, why they don't solve all your problems. There's two things that's going on here. One is that even if you're the only CPU accessing the atomic, you're still sending out these invalidate signals just in case some other CPU has the cache line. And then there's these latency when there really is contention on the variable. And the contention is where it really kills you, if you have a lot of contention. Okay, so atomics are not always the winners. All right, a better solution is to use a reduction operation. This is the syntax that we use in Silk Plus. We create a variable that is called a reducer type variable. And it has a pointer-like syntax. It effectively holds a value. It looks like it holds a value anyway. And you access it using this pointer-like interface. And so what we're incrementing is the thing that we get from dereferencing count R, which is not a shared variable. The thing you get from incrementing the reducer is not a shared variable. I'll get to what's exactly happening in a second. So the important thing is there's no cache ping pong going on here. Each separate thread is accessing its own memory, and at the end, everything's combined together into a single count. So to get a graphical view of what I just said, we have our same calculation here, but now instead of incrementing the count, we're incrementing a view of the count in one thread and a separate view of the count in the other thread. This is all done through the reducer abstraction, which says we don't care from threads. We're writing parallel programs. Threads are something that someone writing producer-consumer or UI stuff worries about. In parallelism, you say, I'm expressing the parallelism. I don't know how many threads I'm actually going to get, but the runtime says these are separate threads, so the runtime figures out how many copies of count I need to make. Okay, so because they're incrementing their own, there's not this invalidation thing. It's not an atomic operation. And the count never moves from its cache line. It just stays in whatever CPU happened to have it last. At the very end, we compute the count here. All right, what is this? Why did I bother writing it out this way? All right, it's pretty clear that the answer is correct, right? We've incremented the thing 5 times, and this adds up to 5. Why did I write it this way? Well, what is the importance of 0 in this case? Can anybody tell me? John?
I think it's the base case, and I think each one is the initialization.
It's the base case, it's the initialization, and why 0? So the neutral value is, it's the identity for addition, okay? If the operation that we were reducing on were, say, multiplication, we would start with a 1. But we're not reducing on multiplication, we're reducing on addition. And so 0 is a special number for addition, 1 is a special number for multiplication, all 1s is a special value for bitwise and a 0 is a special case for bitwise or. So you get the idea. The collection of an identity and the operation is called a monoid in mathematics, and I won't get into it, but the important thing is it's an associative operation. So here you see the parens here. And it has an identity. And they start out, each counter starts out with the identity value, and then we perform an operation, a single operation, repeatedly. And when I say single operation, the operation here is addition. It's represented as increment, but increment is a form of addition. Okay, so this just shows, because it can group this different ways, the number of times that one thread does this operation versus a different thread is irrelevant. You'll still get the same answer. So the load balancing allows you to move things around, and you'll still get the same answer. What you don't get is a correct answer halfway through. This thing does not give us our total count as if it were a serial program. So we're taking advantage of the fact that we don't need the intermediate result, and then the final result is going to be correct. Okay, take a breath here. That was the easy problem. Let's look at now at a little bit more involved problem with what we've already looked at. The nbody problem. We're going to introduce the problem. We're going to parallelize it with loops.
I actually think this is important. I wanted to ask you, it looks the way we just described the problem that given that we've parallelized it, we're willing to do something maybe much less efficient per separate parallel path. Like we're going to go over each pixel and we're going to see a blob of pixels. And for each pixel, we're going to do some calculation like find, is it the center? And we might do that calculation an enormous number of times, but because we have, let's say, a very large number of different processors, we don't care that we're being somewhat inefficient as long as we can parallelize it. Is there a trade-off? You see what I'm saying?
There is sometimes a trade-off. That's not what I'm trying to illustrate here. Okay. And in fact, I will illustrate something kind of like that later. The reason I chose this particular algorithm is because it's really dead simple to understand. Okay, but it is a fair point that if you're looking, if each pixel calculation is looking at all the pixels around it, then wouldn't it be more efficient to sort of go left to right, top to bottom, or go through the diagonal or something like that? And it may very well be. And later on, we'll show a situation where you could actually take advantage of that. Thanks. Okay, so the nbody problem. We're going to describe the problem, parallelize it, and then we're going to sort of go through a bunch of straw man attempts to make the parallel program work right and work efficiently. And then we're going to sort of try a different algorithm that gives you a very elegant way to get around a number of the problems we'll run into. So what is the n-bodied problem? The n-bodied problem is any time you have some number of objects, n objects, and a computation needs to be done between each object and each of the other objects in that set. Okay, n-bodies. So the classic n-body problem is planetary bodies or celestial bodies where each one of them exerts a gravitational force on each of the others. And you compute the gravity between them with this first formula, which should be familiar to anybody who's taken high school physics and remembers any of it. So this is our gravitational element. It's proportional to the two masses and inversely proportional to the distance, to the square of the distance between them. Okay? So that's the force between any two bodies. The force on any one body is the sum of the forces between it and every other body. That's our n bodies. Okay? Our new velocity, if we know the velocity of an object and we know the force on it, we can calculate the new velocity at delta t later using this formula here, okay, which is this f over m is our acceleration times the change, the interval, time interval that we're computing on, and the change in the distance, the new distance from the old distance, the average velocity in that interval times the interval. Okay. If you didn't understand all that math, don't worry about it. The important thing is it's correct. Okay. What we're going to be doing is we're going to be computing this computation, performing this computation for every pair I and j, where I and j are the numbers, elements of our set of bodies. Okay. And then we're going to repeat it for multiple time steps so that we can get kind of a progression of movements. Okay. So here's our illustration of what's going on. Every body has some force on it. That's the capital F, which is the sum of the forces applied by all of the other bodies. And here we have only 4 bodies, but the idea is to be able to calculate for many more bodies. Okay, it has a velocity, and there's a change in the velocity based on that force. So it's going to want to go, this M2 is going to want to go off to the left a bit, right? And eventually, it wants to orbit M1, kind of, right? What we have here is a little video of what happens when we compute 4,000 time steps. And each time step, every 40 time steps, we create a new frame here. So this is just 100 frames total. It's not a real-time calculation. This is not intended to. After all, if this were real-time, it would take years, right? Because these are supposedly planets, and they take years to go around their sun, okay? Or at least a good fraction of a year. But the idea is, anyway, that, we generated a bunch of bodies, we put them semi at random, gave them all kind of a initial motion roughly clockwise, and said, let's go at it. This is a particularly dumbed down version of the n-body problem because A, it's 2D. In reality, if it's gravitation, it would be at least 3 dimensions, right? We're not taking into account collisions. The bodies just kind of pass through each other. Convenient, right? And which also is what makes this a fun problem to work with, because once you've gotten it, then you can start playing with things like what happens if I put some inelastic or partially elastic collisions in there and so on. Okay. So let's look at the general framework. Here's our body structure. You don't have to memorize it, but what's important here is that we have the position and velocity and force and mass of each object. The density and color are really there just for display purposes. Notice that there's an x and y for each of them. That's because, of course, position is a 2-dimensional position, and velocity and force are 2-dimensional vectors, vectors in the mathematical and physics sense of the word, not in terms of STL vectors. So everything has to be computed on both x and y. Our main loop is going to go through and say, well, how many frames do we want to generate? And then for each frame, how many steps per frame, like in the previous animation, there were 40 steps before we generate the new frame. If we didn't do those steps, there would be so little motion within a frame that it would be barely perceptible. A lot of bodies wouldn't even move a single pixel. And then, so for each step, we calculate the forces, and then we update the positions based on those forces. Okay, we have to do these two as 2 separate steps, one after the other, because if we started moving the bodies before we calculated the forces with the other bodies, it would smudge the overall calculation. So we need to calculate all the forces at once and then apply those forces as a separate step. Okay. The central computations here calculate force this is basically the C++ code that does this formula. Should be, it's pretty straightforward. This is our G. We got our masses and so on. I don't think there's anything special I need to, I point out that we compute the distance squared very easily, and we hold on to it before we get the square root, because over here we use the distance squared, so it would be silly to take the square root and square it again. Otherwise, it's a straightforward calculation. Add force is even more straightforward. Takes the force vector and adds it to the current force vector. Okay? So every time we call add force, we're contributing to this sum. We're doing on time. Okay. Good. So we're going to start with the easier of the two parts. Remember, there were two steps. The two steps to parallelize. The first, once we know the forces, how to update the positions, we do this set of calculations. And it starts with shaded here. It corresponds to this formula, updating each of the velocities based on the force that we calculated in the previous step, which we have yet to get to. And this part shaded here corresponds to updating the positions once the velocity has been computed. All right? So this here is our average velocity thing. Take the initial velocity and the next and the new velocity and average them. Okay, so how do we parallelize this? Well, we change that loop from a serial loop to a parallel loop, and we're done. Okay, that was easy, right? Just to show that I'm not chauvinistic about it, this is how you do the same thing in TBB and in OpenMP. Okay, simple parallel loop. All right, now the fun part is calculating the forces in parallel. Again, we'll start with a naive force. Now, I should mention something about this slide. There's an error in this slide. It's a grammatical error. John, you gotta find it. It's got to be here, right? English doesn't have that symbol. Thank you, autocorrect from Microsoft Office. Yes, it decides that naive comes from a different language, and we're going to spell it that way. So, who am I to argue? Okay, so to calculate the forces, we simply have a pair of nested loops saying, let's go through each of the bodies. And then for each of the bodies, we go through each of the other bodies. Or we go through each of the bodies sort of twice, right? Or it's a two-dimensional traversal of a one-dimensional array is what we're doing here. And if they're the same, we skip that. So we skip the diagonal because a body doesn't interact with itself. And then we calculate, we just calculate force and add the force to our running sum for that body.
I don't want to disappoint you. I was on my phone for some time. Give me an uppercase letter for updating the period.
Okay. All right. I'm glad you're on the ball. Okay. So very good. But there's something kind of silly about this. If you know the physics, you know that the action and reaction, for every action there's an equal and opposite reaction thing, right? We calculate the force that body body J is exerting on body I and adding it here. But that same force is being exerted by body I on body J. So why are we computing it for I here, and then sometime later we're going to compute it for the opposite one? So here's a better implementation. We're still serial here. It says, well, once we've computed the force in one direction, we'll just take the opposite force and apply it in the other direction. Very good. So we do that simply by saying we're just going to start iterating from I plus 1, so we don't cover the ones that we've already computed. And what we're doing is, if you want to look at it graphically, is here's I and J. We're computing this upper left triangle of the total iteration space, okay? And back from our middle school geometry, the dotted line means it's not included, okay? So just the shaded part. Good. So we've cut the effective work in half, almost in half. Why? Because the thing that we're the calculation that we're saving is the most expensive calculation in the entire program, which is the square root. Okay, and there's a couple of multiplications in there as well. So that's where all the computation is done. It's not a lot of computation, but it's basically all there is. So now what happens when we go parallel? Well, we changed the outer loop to a parallel loop. Now we could have changed them both to parallel loops. And that would increase the amount of parallelism, but probably beyond the resources we actually have to take advantage of it. And it would make the problem I'm about to point out worse. So given that we're about to find a problem, let's not aggravate it in advance. Okay, so we made the outer loop parallel. So we're calculating, calculate force, which is our expensive calculation, and add force in parallel. What's happening if we look at this as a directed acyclic graph? We start before we enter the loop. The outer loop is shown as these parallel strands, okay? So we're doing the calculate force for I equals 0 in parallel with the one for I equals 1. And then in serially, within each iteration of the parallel loop, we're calculating for j is I plus 1 and j is equal to I plus 2, and so on. Anybody see a problem with this? Yes? Cache coherency. It gets worse than that. The inner loop goes smaller and smaller. You know what? That's not actually a problem because the load balancing is going to be automatic. So what's going to happen is the one CPU will simply execute, will get done faster, and then it will start on other iterations of the loop. So that's not really a problem. Anybody else? There's a race. Thank you very much. Notice that we're adding to the element 1 here and here and here. These two do not race with each other, but they both race with this one. They're taking place in two parallel strands. They could happen concurrently. So that's a race. There's another race here just shown on this slide, which is between this one and that one, okay? But really, there are close to n races here. Lots of races. All right, so how do we get rid of the race? Well, let's try the same solutions that we tried for the stars problem. But first, let's try mutex, right? Anybody says a race? Anybody from the concurrency world knows that if you see a race, the first thing you do is go to the shelf and you grab a mutex. Well, we could do that. We could embed a mutex here, and it better be pretty small because we have thousands of bodies potentially, right? So we'll do this thing that's called a small mutex. And you know, we're doing very little work in the critical section, so we'll just use a spin lock, which is efficient enough for our purposes, generally. And then within the actual computation, we'll grab the lock on I, and then we'll do our add force, and then grab it on J and do our add force. This will work. This will fix the correctness problem that the race caused. But you should know that mutexes are not cheap. Even a spin lock has that same problem of the bouncing cache line as as we did with the race in the case of not the race, I'm sorry, the atomic in the case of the star counting. Okay, so spin lock is not a panacea. It's got the same problem, and it's got the same area where it works, which is to say when the contention is low enough, it's fine. Okay, we mentioned atomics. Why not use atomics? Well, here's a straightforward attempt to try and, I'm sorry, I left out a step here. The previous example showed a mutex per body, and I said that could get kind of expensive, even with the mutex, even with the small mutex here. What if we wanted to reduce the total number of mutexes because of memory pressure? So we could actually do this, and this is a technique that is used more in concurrent programs than in parallel programs to have some limited number of mutexes for a very large data set. And that is that we create here just 64 mutexes, and it's static, so there's just one array of 64 mutexes. And then each body's mutex is effectively a hash into that array. Now, does that mean, now each body doesn't have its own mutex. Is that a problem? A little bit. When more than one body shares a mutex, you get more contention than you would otherwise. But it is correct. You'll get correct behavior from the program. You'll just be locking mutexes more often than you want to, or hitting a lock even when there's not a real collision. Okay? And so this is the same program here, basically, but using the mutex that we get as the member from the member function. Okay. Interesting technique, useful, not great in this situation. Atomics. So our first attempt at atomics doesn't work because though we replaced our force vector with atomics, we can't add to it atomically because there's no such thing as plus equals for atomic floats. And the reason there isn't such a thing is because most hardware, in fact, I don't know of any hardware, supports it. Right? They support atomic addition, but not atomic addition on integers, but not atomic increment of floating point values. So that's not going to work. So you end up having to write something significantly more complicated, and believe me, I took more time than I should have trying to get this right. Okay, and I don't have proof that I got it right because I did not actually compile and test it. So this is comparing exchange week, but if I got it right, it's not that bad, but there's a loop involved. Okay, so you can imagine potential, if there's a lot of contention, there's a performance hit to be taken there. And you still have that ping-ponging cache line problem that we were talking about before. So here's a counterintuitive solution. How about we undo that optimization we made earlier and compute only do the add force only to the I dimension and do the full traversal here. So full rectangular traversal or square traversal of the traversal space instead of that triangular thing we did before. This will solve the race because for each parallel iteration along the I dimension, only one body is being updated. Okay, no two iterations are updating the same body. That's actually the correct way to say what I'm trying to say. Good, so it solves the race, but what about doubling the work? Well, what's doubling the work when you're saving cache ping pong? The answer is, I don't know. You actually have to measure it. This may actually be faster than using atomics or mutexes, even though we doubled the work. Now, obviously, if you have fewer than 2 cores, fewer than 2 cores. And if you have only 1 core, which is another way of saying fewer than 2, obviously, this is going to be worse than this serial program. If you have 2 cores, it's still going to be worse because you're doing twice the work, but you're paying some overhead for notating it as parallel. Not a lot of overhead, but some. At 3 cores, you're probably doing better than break even. And if it's the best way to write the thing, then maybe if you've got 1,000 cores, this is the way to do it. Remember that 1,000 cores, not only can you absorb that factor of 2 loss to some degree, because you're still getting a 500x speed up, but cache ping pong is much worse with 1,000 cores than it is with 2. So it may depend on how big your machine is, whether this is the better or worse approach. Okay, but is this the best we can do? Well, at this point, let's take a breath. And remember why we're here. No. Okay. And let's look at a different way of solving this problem, of solving the race problem. And let's see if we can even get our factor of 2 speed up back. Okay. Let's take a little break from the actual program at hand and look at a general problem of cache locality. Here what we have is a pair of nested loops. It's part of the nbody traversal. We're doing a 2-dimensional traversal as we saw before. So when you have a specific I, we're going through the array for j. Okay, so the first j we see is 0. And so we read body 0. Body 0 gets moved from main memory into the cache for the L1 cache for the CPU. Okay, it just so happens that the body structure is just about one full cache line. In fact, the way I actually defined it, it's even bigger than the cache line, which is pretty horrible. But so it's going to, let's say it's one cache line. So this takes up one cache line, and then when j is 1, it reads 1 into the cache line, then 2, then 3, and so on. We get up to 1,000, and now our cache is full. So what happens when we get to 1001 is we get to evict something from the cache. And there goes element 0. And then, so we put 101 where 0 used to be. 1,000, sorry, 1,000. I think I'm off by 1. Oh no, 1,000's here, and 1,001, right? 1,001 where 0 used to be. And then when we want to read 1,002 in, we have to evict something else. And it's more or less the least recently used, so there goes element number 1. Okay, and now this is our cache at the end of the first iteration. But now we're immediately going to start at the beginning again with I equals 1, right? With the next version, with the next value for I. And we're going to start reading j's in again. Wait a second, 0 was in our cache just a nanosecond ago, but now it's gone, and we have to read it from main memory again, and that's really slow, like it takes nanoseconds. So there again, we're evicting something that we're about to read, which is really fun, right? That's great. And read in something that until a short period of time was available to us. So what's happening is the cache is really, it's like not doing any good at all, right? And the pattern here that you should learn to recognize is that we are running through memory. We are going sequentially through a large enough chunk of memory that by the time we get to the end, the stuff at the beginning is long forgotten from the cache. Why is this a specialist issue for parallelism? Well, it's a problem for serial programs for sure, because the CPUs are faster than memory. But 2 CPUs are even that much more faster than memory. You still have this kind of little narrow straw between the 2 CPUs and our memory. So the more CPUs you got, especially on a single socket, the more this cache thrashing hurts you. Let's go back to our stars program for a moment before we go back to our nbodies and say, well, the cache problem affects the stars too, because remember that we're seeing all the pixels around. So if we saw one pixel, and then after going through all the row, we come back to a pixel that we already saw, it would be nice if it were still in cache, right? So the way to solve this problem is we'll divide this into tiles. And what a tile is simply is a chunk of our traversal space. It could be 2-dimensional, it could be 3-dimensional, or it could be n-dimensional, really depends on what your traversal space looks like, where all of the memory that you are reading in for that tile will fit in cache. That's your ideal tile size. If you can't figure out your ideal tile size, go for a small tile because that you're sure will fit in cache. That's the idea. So now if we were to traverse this, what we would do is we would traverse a tile at a time. So we're incrementing by tile size here. And then within the tile, we do the same old serial algorithm we were doing before. Okay? But we're traversing in parallel the tiles. So we're saying we're going to do this tile in parallel with that tile over there. But within the tiles, we don't need to go parallel because we have enough parallelism just doing all the tiles. We could do parallel within the tile. The problem with doing good parallel within the tile is now you've got different CPUs, which means different caches, and it's not clear you'll get any win at all. Okay, so that's tiling in the simple case. Can we do something with the n-body problem? Okay, can we do it? And can we get our triangular traversal back? That would be nice too, right? So the answer is yeah, we can, but not quite in the same way as we did with the stars. We can divide this into tiles, but the problem is that the tiles aren't independent, at least not in this simple grid. these two have the same range of I values, and we know that when the I values overlap, you get races. So we need a different way. How about we tile it in this kind of recursive way? What we have here is our triangular traversal, and we've divided it into 3 big tiles. In order for 2 tiles to be independent, to be in parallel with each other, this is the condition that has to hold. The I range of one has to not overlap the I or J range of the other. Okay, because we're updating both the I and the J elements. So it can't overlap either of the ranges. And that also means that if you transitively apply this, it means the J range of one can't overlap the I or J range of the other as well. Okay? It doesn't even have to be stated because it's automatically implied by this statement. Okay, so in this case, the triangles are in parallel because they have disjoint I and J ranges. But they are not in parallel with the square or the rectangular piece here because they have overlapping I and J ranges. Okay. Given the time constraints, you may have to, it took me sitting, at least 2 minutes to completely absorb that. But trust me, these don't overlap and these do overlap. Now let's recursively apply the process of tiling at the next level down. So we take each triangle and we divide it into the same 3 tiles that we did before, but now each of the tiles is smaller, right? And again, these 2 are in parallel, and they're not in parallel with the square. But now we've also subdivided our square into 4 squares. It's really a rectangle. It's almost square, but there's a divide by 2 round off that happens so that one may be one larger than the other, in one dimension or both dimensions. So in this case, the formulation is still the same. They have to have non-overlapping I and J ranges. And it just so happens that for anything in this quadrant, the I range will not overlap the J range. So you can forget about having that problem. And now you only have to worry about the I range overlapping the I range or the J range with the J range. And as a result, you discover that these 2 diagonals are in parallel. They don't overlap. And these 2 diagonals are in parallel. They don't overlap. So you can do 2 in parallel, sync, then do the other 2 in parallel. Okay? Same thing with the triangles. You do 2 in parallel, sync, and then do this one. And because it's recursive, remember that when you do this one, it may look like one big square, but it's going to be recursively subdivided. So this is what the algorithm looks like. I'm going to explain cache oblivious in a second, what that means. But the algorithm looks like this. This will start with a triangle. So the outermost thing, calculate forces, is simply calculate the forces for this triangle. So it's just a single call to our little triangle, which is our recursive routine for triangles. And what's happening here is we're dividing the range in half and spawning the triangle to do one half and the triangle to the other. So these 2 run in parallel, the 2 triangles. Then we sync. We have to sync so that neither of these triangles is still being computed when we get down to computing in a rectangle. Is everybody clear on that? It's really important that that sync point be there so that you don't have parallelism where it doesn't belong. The square is kind of the same thing. It looks like a lot more code, but it's actually it's the same concept, which is we divide our ranges in half, and we calculate the 2 A squares and do them in parallel. Then we sync, and then we do the 2 B squares in parallel. Again, because the A and the B cannot be in parallel with each other, we have to sync. Now, we also have a base case. At some point, we get down to a single body, right? And at that point, we calculate, not a single body, a single I and J. And at that point, we compute the forces between body I and body J and store it. And this is not going to happen in parallel with anything else. It'll happen in parallel with updates on different bodies, but it will not happen in parallel with updates to the same body because of the way we've recursed down to the thing. So what does it mean that this is cache oblivious? Well, we're doing recursion, but And at each level of recursion, we have a smaller and smaller data set until our data set ends up as being a single point in our two-dimensional space. That's going to fit in cache. Okay? In addition, the next n levels up of recursion will also fit in cache. And so once you have crossed that threshold into being small enough to fit in cache, it all goes very fast. But notice that nowhere in this code did we actually specify the cache size. It's oblivious to the cache size, and that's what the term cache oblivious means. Cache oblivious algorithms are useful in both serial and parallel programming, but as I mentioned, cache effects are magnified when you have multiple cores. So you want to use it when you can. Question?
There's still, when you're below the cache, you're still spawning and syncing, so there's more overhead than there really needs to be, right?
Good point. All right, so the question was, when you're below the cache, when you're within a single cache line, or sorry, not a single cache line, when you're small in a data set that's small enough to fit in cache, then all of this spawning and syncing and recursion is wasted, extra work, right? It's not completely clear because depending on how many CPUs you have, you may still have resources left to exploit. So you may want to continue recursing down and syncing, but at a certain point, you will have so many grains going on at the same time that you have more parallelism than you have CPUs. And you need more parallelism than you have CPUs in order for the load balancer to do its job. But once you get more than about 10 times as much parallelism as you have CPUs, then any additional parallelism is unnecessary. And I don't know if I mentioned it earlier, but spawns are cheap. The idea is you want to be able to put spawns in your program as often as possible so that if you go from your lowly 2-core circa 2010 laptop into a 15-core server somewhere, it'll get that speed up automatically, right? So you want to put more parallelism in than you can exploit, but it's not free. Even though it's cheap, they're not free. So there is something to be said for trying to cut back on the number of spawns to a degree once you know that you've saturated the parallelism. And similarly, recursion is a bit more expensive than iterating. And so even if it were serial recursion, you would like to avoid it. And that was a great question because my next slide addresses it. All right. There was a question back here, though. Okay, great. And that is, what we've done here is we've done a process called coarsening, where at a certain point, and we've specified our threshold here at 16, but the threshold is best determined by experimentation, that once we have gotten below our threshold, the size of the rectangle or triangle that we are traversing is below our threshold, we switch to serial. Not only have we switched to serial, but we've switched to non-recursive serial. We've switched to a loop. Okay, so this is our old serial program rewritten down, but only for the smallest tile in our set. Question or comment?
Just to clarify the notation, the sinks apply to the spawns within the same scope, or
No, they apply to the sinks.
Under spawns, bigger spawns are implied while we're here, and a lot of spawns will be generated inside this direction.
Ah, good.
Right,
so here's the question. That's a good question. All right, so what is the scope of the spawn, of the sink, I'm sorry. The sink applies to any spawns in flight within this function. So if there's bigger spawns ahead of here, like this entire routine probably has been spawned, okay? All but the first iteration, no. Yeah, all but the first invocation of this routine is spawned, okay? Whatever is happening in parallel with this continues to be in parallel with this. The sink does not stop that. It's completely modular. And that's one of the design goals of Silk Plus and of many of the other parallel systems that we've got. Question?
The sink applies to, does it apply to anything within, or any spawns in flight in that function, or within the scope?
It's, in the case of Silk, it's the whole function.
Okay, so even if you spawn things outside of that and in the scope, so the same function,
That's,
that sink will apply.
that's correct. That's correct. it's not important to this. It's not important to this example because we're staying within the same scope. But it is worth noting that if I had put a spawn up here, this sink would have synced with it. Okay. There's a couple of places where in Silk where a new task block is created. There's a term for it, the task block. So there's 3 task blocks in Silk plus a function body is a task block, a try block is a task block, and the body of a Silk 4 is a task block. So within each of those, the sinks are strictly limited to the things that happen within that task block. Okay, but the function is the one that we normally think about, and that's important because you need to be able to do a spawn in a conditional without it having automatically syncing at the end of the if, right, and things like that. Okay, good questions about Silk, but the point here is about the parallelism in general. So what we have here is coarsening, which is the final optimization that we're doing today on this code. All right, and this is quite fast. It is very parallel. It'll saturate your CPUs and use them very efficiently. Can we do better? Can we do more? Well, you can always do more, right? I mean, pretty much. One really important optimization we did not attempt was to restructure our data structure. The data structure of a structure containing a bunch of doubles and an array of those is a very easy to understand structure, but it's terrible for vectorization. What the vectorization would like to see is a struct containing a bunch of arrays instead of an array containing a bunch of structs. Okay, there's acronyms for that too, SOA and AOS, array of struct or struct of array. Okay, and vectorization, which is this ability to execute one instruction on multiple pieces of data at once, likes to see all the data contiguous in memory. So if you're operating on fx within a single body, you would like all the fx's to be, the multiple bodies, sorry, in multiple bodies, you want them to all be contiguous in memory rather than in the middle of a struct, in the middle of the next struct, in the middle of the next struct, okay? Vectorization can do that, but it's much slower. That's a gather operation as opposed to a contiguous load. So that's one big optimization we left out here. And we could have gone into it, but I don't have time to either write the slides or present them. To really figure out what you need to do to make a parallel program run best, you got to measure it. You got to measure. You got to figure out where is the parts where the program is slow in the serial case. There's no point in parallelizing a part that's not taking up much time. Where are the bottlenecks in the parallel case? You need to use sometimes sophisticated tools like Intel has vTune amplifier, which actually can read the special registers on the CPU that measure how often did we get a cache miss, and other kinds of things like that that are really hard to judge. Sometimes your program is like, it's running full tilt, the CPUs are pinned at 100%, and you're getting lousy performance. What's going on? It could be a memory bandwidth problem. And you can sometimes figure it out by reasoning through it, but the tool will get you there much faster. Just like you can use printfs or you can use a debugger, and the debugger will usually get you there faster. The other thing about measuring is you can do some guesswork. You can even be pretty darn sure that you've got the faster thing, and you could be wrong. Okay? So the whole thing about using the atomics, or should we just double the amount of work we're doing so we can avoid the atomic crash entirely? I don't know which is faster. And in fact, the answer may depend on what hardware I'm running on and how big my data set is, things like that. So parallelism is about decomposing a problem. It requires some creativity. So it's kind of this really a mixture of art and science. There are techniques. That's the science part. But it's a programming problem. It's an art, like programming is. Even if you have a correct implementation that gets the correct answer, it doesn't necessarily mean that you are getting you can have practical effects like cache effect and contention. And then the last thing is measure and do this as an iterative process. So that's it for this talk, so I can stay for a few more questions. How do we handle exceptions? Well, that depends on the framework. In the case of Silk Plus, it remembers the exception that would have been the first one if this had been a serial program, and it throws it at the appropriate join point.
Small point so people aren't confused, the CPU cache doesn't use an LRU algorithm.
So it does not use an LRU. Okay, thank you. So the cache, it's more complicated than that for sure. But there's certainly cache eviction effects. Yeah.
So you described the algorithm as cache oblivious, but you're setting an arbitrary threshold. I've actually implemented this, and I set the threshold, and it's essentially a function of the size of your cache.
Yes.
Right? You basically set it so that you're working on a block that exactly fits inside your cache.
That is correct. So you could certainly take a cache oblivious algorithm and you could make it cache aware by doing enough experimentation or taking advantage of some knowledge of just how big the cache is on the machine you're using. Generally, what you do when you set the threshold is you set it small enough that you're guaranteed to be in cache of any reasonable architecture, modern architecture that you might be running on, but big enough so that it actually has some effect. And there's a diminishing returns. As you make the threshold bigger and bigger, the advantage you get every time you double the size of the threshold is it gets less important. So the first 16, as we showed, makes a big difference. The next 16, the threshold going from 16 to 32, that might make enough of a difference to make it worth it. From 32 to 64, my experience is around 64 is about where it tops out and you stop noticing the effect very much, even though that may be smaller than your cache. So it's not 100% accurate to call it cache oblivious, but it's pretty close. And if it's within the size of even the smallest machine you may be running on, it'll work well on bigger machines that have bigger caches.
Thank you.
Sorry, just maybe a two-part question. Can you give us some intuition on the cost of Silk Spawn? And also, how expensive is the runtime itself?
So Silk Spawn is between 5 and 10 times the cost of a normal function call in the Intel implementation. The original MIT implementation was slightly faster, but it involved the inability to call back and forth between normal C and Silk, and we paid the penalty instead to make that compatible. Still looking at ways to make it even cheaper. The steal is where the expense is. We haven't talked about work stealing, which is the scheduler, the runtime scheduler. If you do a lot of thrashing, if you're spawning off a lot of really small bits of work, that steal overhead could be significant. I'm not exactly sure how to quantify it. But that is where the expensive part of the scheduler is. And that is another advantage of recursive algorithms, is that they spawn off big chunks, and then when you get down to the leaves, or not even to the leaves, but halfway through the recursion, there's no more, all the CPUs are saturated, there are no more steals, so you're not paying the overhead of steals, okay? Whereas if you were to like spawn in a serial loop, you're constantly stealing because you're spawning something short, it's done, and now that CPU becomes idle again and it has to steal again. So there's all sorts of techniques there that we didn't get into, avoiding spawning off too small chunks of work. The one other thing I should mention about the overhead, I lost my train of thought, so sorry. Thanks.
Well, I know people want to leave, so I'm going to just try to be the last person. I want to thank Pablo very much because I learned a lot in this session, but Pablo, I am troubled about something. You've mentioned the races a number of times in this session, right?
Yes.
And that having lots of races is not a good thing, right? Well, doesn't that by definition make you a racist?
Yeah. Yes. We have a tool, we have a set of tools that we call race detectors. So it'll tell you what your genetics are pointed at you. The race detector will do it. So thank you very much for coming.